Okay, so good evening, everyone. My name is Devarun Banerjee. I'm a PhD PMRS scholar of Indian Institute of Technology, Delhi. Okay, so good evening. Uh, my name is Devarun Banerjee. I'm a PhD PMRS scholar of Indian Institute of Technology, Delhi. Live session on NPTEL course Waste to Energy Conversion. The first assignment would be based on a problem, numerical problem. So in an MSW gasifier, the air flow rate and feed flow rate are 10 nanometer cube per second and 8 kg per second. The MSW does not contain any sulfur, nitrogen, or chloride. The syngas contains carbon monoxide 35%, CO2 3%, hydrogen 40%, methane 5%, and C2H2 3%. So to calculate the rate of production of syngas in normal meter cube per kg of MSW, the four options are given as 9.0535, 7.0535, 5.0, 3.0535. So it's a simple problem. So the rate of production of syngas as a formula, as a correlation with the air flow rate and feeding rate, it equals to the air flow rate in normal meter cube into 0.79, 0.79 being the nitrogen content in normal air, divided by 1 minus the summation of all the constituent gases CO, CO2, H2, CH4, C2H2 divided by 100 multiplied by feeding rate in kg per second. So if you just put the values, air flow rate is given as 10 normal meter cube per second, 10 into 0.79 divided by 1 minus 0.303 would be the CO2, 0.4 would be the H2, and 0.05 methane, and 0.03 C2H2 into 8. 8 is the feed flow rate. Just calculate it, it will be 7.0535 normal meter cube per kg. Okay. Second question is, pine needle is used to produce bio oil in a slow pyrolysis unit. The percentage of bio oil, char and gas is 40%, 45%, and 15%. The average molecular formula of biochar is determined as CH 0.56 O 0.28 N, and for bio oil it is CH 1.47 O 0.36 N 0.005. The composition of the gas is as follows: hydrogen 15%, CO2 44%, CO as 25%, CH4 as 16%. So calculate the percentage of carbon converted. So if let us see the solution of this particular problem. So if you have to take a basis. So I have taken the basis of 100 grams of pine needle, the biomass source which is given here. So it is told that quantity is 40%. The biochar quantity and the gas quantity is also given, right? So biochar quantity is 45% and gas quantity is 15%. So based on our basis, 40 grams would be bio oil, 45 grams would be biochar, and 15 grams would be the gas, right? So the bio oil molecular formula is given CH 1.47 0.36 N 0.005. So weight. So the molecular weight is coming around 19.3 gram per mole. So we are getting about 40 grams of bio oil, which means to divide it by molecular weight, you will get it in terms of moles. So you're getting as 2.0725 moles of bio oil is produced. The same way, for the biochar is also calculated. The 2.613 moles of biochar is formed, and for gas, the molecular weight gas will be calculation. So so 15% hydrogen, 44% CO2, 25% CO, 16% methane is shown as the composition of the gas, right? So based on that, we calculate the molecular weight. 0.15 into 2, 2 is the molecular weight of hydrogen, 28 is of CO, 16 is of methane. So a similar way, we are getting as 0.513 moles of gas is formed by the pyrolysis. Now, so in the bio oil, what is formed uh, in there is a stoichiometrically for entirely 1 mole of bio oil, there is 1 mole of carbon is present. So directly the carbon present is bio oil is the same is as 2.0725. In the similar way, for the biochar also this thing actually stands, right? For biochar, the composition if you see, it is the one mole of carbon is there for 1 mole of biochar. So similarly, for biochar is same as 2.613 mole of carbon is there. For gas, it is interesting, like because there is not 1 mole, rather you have to summarize. So summarize them. So summarize them as 0.44, 0.25, 0.16, and multiplied it by the with the moles of the gas formed. So that will be the total carbon present in the gas. Summarize all of these carbons. This will be the total carbon, and for in will be the what we have got, right? Is 2.0725. So 2.0725 divided by 5.1. This is the summation of all the carbons in the product into 100%. That will be your answer, 40.468%. Okay. So basically, these are the some sample tutorial problems I discussed in this week's lecture. The densification of solids basically was mainly focused upon. So the contents mainly comprised of uh, what is densification, the fundamentals of densification, types of briquetting processes and their comparison, carbonization process, carbonization reactor, briquette characteristics, application of briquettes, manual briquette machine. So densification is basically the process of increasing the density of something. So it makes a fuel denser and more uniform properties with respect to its raw form. So when you're talking about the waste to energy conversion, it means that a particular thing we want to use it for the energy purposes, for fuel purposes, which means that we need to have a maximum energy density, right? So for that we need to make the density of a particular source higher. For that we need to densify it via different procedures, which which include the safe steps like compaction, compression, concretion, concentration, like that. The advantages are simplified mechanical handling and feeding, uniform combustion in boilers, reduced dust production, reduced possibility of spontaneous combustion in storage, simplified storage and handling infrastructure, lowering plant, reduced cost of transportation due to the increased energy density. These are all the advantages. However, the major disadvantages to the biomass densification technologies is a high cost associated with some of the densification processes. And obviously, lots of research are ongoing to optimize those cost problems. So the densification of biomass under high pressure results in a mechanical interlocking and increased adhesion. Right? So basically, when you're putting some particular force, then what happens is there will be a mechanical interlocking based on some molecular forces such as van der Waals forces, and the solid particles will get interlocked or based on some adhesion or cohesion, which form intermolecular bonds in the contact area. Okay. So when the material is compacted with low to moderate pressure, low to moderate pressure means that point, then the space between the particles is reduced. Okay. So the one question is, which of the following statement is not true about densification? It provides simple mechanical handling and feeding. It provides uniform combustion in boiler. It reduces the cost. It increases dust production. So the correct answer is it increases dust production. So obviously it's not true because densification obviously reduces the dust production. As already discussed, it comes under one of the advantages of densification process. So a few more points about densification. So if the pressure is increased at a certain stage particular to each material, then the cell walls of cellulose constituent are collapsed. When you're trying to densify it with a very high pressure, then it might be happening that your material might get collapsed. So that particular optimization is also important to maintain your material's characteristics as well as increasing its energy density. The pressure required to achieve such high densities are typically 100 megapascal plus. So if you are going beyond that particular uh, result in collapse of your material structure. A binding agent is often necessary to prevent the compressed material from springing back and eventually returning to its original form. So that is also an important point. Obviously, particular binding agent is can prevent basically to retain your briquetted or densified material to not again loosen up. Additives of highly viscous such as tar, molasses, and other molecular weight organic liquid can form bonds very similar to solid bridges. The binding agent can either be added to the process or when compressing ligneous material be the part of material itself in the form of lignin. Simple thing. The resulting solid after the densification is called a briquette if roughly it has a diameter. Smaller sizes are normally termed pellets, though the distinction is arbitrary. There is not a particular distinction like if it's a particular diameter, if it's greater than that or less than that, it will be briquette or it will be pellet. But it often is usually termed like that. Usually the greater version or the thicker version, uh, the bigger one, smaller ones are usually called as pellets. So the next question is the most important factor in the binding process of biomass densification are moisture content, bulk density, thermal properties, or all of the above. All of the above, the physical properties of the biomass such as moisture content, bulk density, void volume, thermal properties are all the most important factors in the densification process, particularly the binding process of densification. Okay. So the ultimate density of a briquette will depend to some extent on the range of factors, including most importantly the nature of the original material and the machine used and its other minor factors. So the based on compaction, the briquetting technologies can be divided into high pressure compaction, medium pressure and low pressure. Usually high pressure processes releases sufficient lignin to agglomerate the briquettes, though this may not be true for all materials. Intermediate pressure machines may or may not require binders depending on uh, and the low pressure machines invariably obviously require some binders. Okay. High and medium pressure compaction normally does not use any additional binder. Normally the briquetting process bases either on piston press or screw press technology. Other briquetting technologies are less applicable in developing countries. So basic the main fundamental briquetting in countries like us, India, are like piston press or screw press kind of technologies for the densification purpose. So the next question is based on compaction. The types of briquetting technologies are high pressure compaction, low pressure compaction with a binder, medium pressure with a heating device, or all of the above. So the correct answer is all of the above: low pressure and medium pressure. All of these are types of the briquetting technologies, as already discussed. Okay. Among them, the piston presses is one of the briquetting methodologies which are used. Piston presses punch the feed material into a die with very high pressure, either mechanically powered by a massive flywheel or by a hydraulically driven piston. And also, the screw press is also another type of machine which works based on a high and medium pressure operation. So in the screw press, the rotating screw takes the material from the feed port through the barrel and it compacts against a die. It's a little bit different between the this type of two, one piston and one is the screw press thing. Okay, so the performance of the process, it depends on the flow ability and cohesion of the feed material, particle size and distribution, surface forces, adhesiveness, like that. Screw presses produce high quality briquettes with homogeneous structure and good combustibility. But very little maintenance. However, the main disadvantage is that the wear of the screw leads to elevated spare part cost. So it gradually gets corroded and gradually gets depleted. So that is why this particular spare parts cost is there certain amount of which we need to change it periodically. Okay. So here some the comparison between the different densification processes are shown. Like screw press, piston press, roller press, pellet mill. You can check this, check the lecture videos for and check the slides basically for the this kind of raw data. Okay. And apart from the briquetting process, uh, so although the briquettes can be used directly as a fuel, the burning of briquettes have some demerits, such as it increases the generation of smoke, it has a lower heat value, it has a reduced ignition and burning properties, and it is not very much. That is why some carbonization is usually done, which is a partial pyrolysis process where under inert atmosphere your material is heated up to 600 degrees Celsius and burnable gases like CO, CH4, H2, formaldehyde, methanol, formic acid, acetic acid, these are formed, as well as some non-burnable gases such as CO2, H2O. Okay. So the carbonized briquettes can be produced from agricultural two possible production sequences. So either you can go for initially the carbonization and then the carbonized material we can grind and briquette and then use for fuel purpose, or on the other way around. First grind them, make it dense, then carbonize it, and then so two of the processes are uh, can be used. So here are the some changes of the properties as a result of carbonization are shown. So and the chart, which means that after the carbonization, what is happening? So the fixed carbon content is actually increasing. volatile matter, moisture content, these are decreased in the pine needle char or any kind of char. This is very common thing, and there is a certain amount of that. So the next lecture of the densification, it talks about the different carbonization reactors, such as the coarse material or fine material. For the working of this particular coarse and fine material, we need to use some different types of reactors actually. Okay, such as the continuously working shaft furnaces, or for fine materials, some rotary key vessel. So basic carbonization reactor such as the continuously operating shaft furnace schematic is shown here. Okay. And apart from that, the briquette characteristics are also discussed. So the briquette characteristics are basically of two kind of types: the briquette handling characteristics and fuel characteristics. So briquette handling characteristics involves the friability, resistance to humidity, etc. So your product should not be crumbling, and it should not disintegrate when handling and the storing, the transportation, these things are being carried out. Okay? And the food from fuel characteristic point of view, its heating value, size and shape, these are actually very much important properties of the uh, particular briquette. Okay, so the next question is, mechanical piston presses and pellet presses make briquettes with densities in the range of what is the density, 1200 to 1400, 1500 to 1800, 1600 to 2000 kg per meter cube. So the correct answer is 1200 to 1400 kg per meter cube. So can be seen that The high pressure processes such as mechanical piston press, pellet press, and some screw extruder are able to make briquettes which are having a 1200 to 1400 kg per meter cube density. Yeah. So density is one such important characteristic uh, which we measure basically the property of our particular densified material. Okay, and here are some examples are shown before briquetting and after briquetting. What is the terms of the volume and bulk density of different particular biomass sources. And then another important property is the friability. So friability is a measurement of the briquette's resistance to mechanical action that can affect them during handling and transportation. Okay, so generally the briquettes which are produced by mechanical piston presses and screw presses are hard enough to be transported by lorry for considerable distances. And another important factor is the resistance to humidity. So obviously your material should be resistant enough to be transported and to be acted under humid conditions. So the inherent binders and most externally added binders are water soluble. So briquettes and pellets have to be stored under cover and they do have a limited lifetime under humid conditions. Okay. So next question is the friability index value of dash indicates that the briquettes are disintegrated entirely after a certain time. 1, 2, 0, 10. The correct answer is 0. So the friability index of 0 indicates that the briquettes are disintegrated entirely after a certain time, which indicates an inadequate briquette quality. Okay. And apart from that, from the fuel characteristic values, heating value is one of the very important parameters. There has been a detailed discussion of on heating value in the earlier lectures. You can check that how it is determined. Basically, experimentally determined via the bomb calorimeter, and some empirical relations are also there from based on its ultimate and proximate analysis data. So those empirical relations to determine the heating values. Okay, and some basic applications of briquettes such as in boilers, in the biomass gasifiers. So basically, this energy production and all, and different other heat production, burning equipment. So these kind of applications are there for the briquettes. And one sample problem is based Uh, a 10-ton hydraulic jack was used to lift the machine components and compress the briquettes. The compaction force can be calculated using pressure. Pressure read from the pressure gauge connected to the hydraulic jack. The compaction pressure is 17.5 kilonewton per meter square. So the machine has 30 molds and the diameter of the briquette sample is 25 millimeter. You have to calculate the compaction force. So let us see how to solve this problem. Compaction force is basically a multiplication of compaction area and the total compacted area. Okay, so the compaction force is a compaction pressure multiplied by total compacted area. So the pressure is already given, 17.5 kilonewton per meter square. Then we need to calculate the total compacted area. For that, uh, it can be computed by multiplication of the number of briquettes which can be produced at a, to the cross section area of each briquette. So it is shown that 30 molds are there, which means that 30 briquette can be produced for a certain time. So 30 multiplied by cross sectional area of a briquette. So simple for a sphere, so it's pi d square by 4. D is the diameter. Diameter is given is 25 millimeter, so 0.025 meter. So pi by 4 0.025 square into 30. So 0.147 meter square is coming. You you multiplied this particular area with the compaction pressure. So compaction pressure is given in kilonewton. So I multiplied with 1000 to convert it into Newton per meter square. So 17.5 into 1000 into 0.0147. So it is coming around 257 Newton. Okay. So that will be the compaction force. And the last lecture of today, this week's discussion, this was based on the efficiency improvement of power plant. Some basic power generation flow sheet was discussed. Some basic, you can check that basic process flow sheet for the power generation in a plant. Okay. Uh, Based on that, I would like to ask this particular simple question, that the overall energy production from a waste to energy plant depends upon uh, heating value of the waste, thermal efficiency of the boiler, efficiency of the turbine generator, or all of the above. So the correct answer is all of the above, because the overall energy production from a waste to energy facility depends upon heating value, the efficiency of the thermal processing unit, the thermal efficiency of boiler, efficiency of turbine, and all are the important factors. And some basic the performance of a power plant, it can be actually numerically expressed via different parameters, such as one such as heat rate, fuel energy input to the electrical energy input output, how much fuel energy you are giving as input, and from that how much basically electrical energy you are able to obtain from our particular power plant. Thermal efficiency, actually based on that, there is one question. The thermal efficiency of waste to energy power plant can be expressed as, there are these particular four options. uh, Thermal efficiency, energy input into time by MC into CV. MC is basically quantity of fuel by fuel consumed. CV is calorific value of feed. Or thermal efficiency equals to energy generated into time divided by MC into CV. Or it is energy generated into MC divided by CV. Or it is energy generated divided by MC into CV. So basically, not wasting further time, thermal efficiency is basically ETA. It's indication of how well the plant is being operated as compared to the design characteristics. So thermal efficiency ETA is equals to energy generated into time divided by MC into CV. Okay. And for further, you can basically correlate your thermal efficiency with heat rate by further calculations. It equals to 100 divided energy input supplied by the fuel to the power plant divided by energy generated. So you can express in this way also, which means that equals to 100 by heat rate. Okay. So a simple problem is also discussed. So if the average heat rate for the power plant is 2611 kilocalorie per kilowatt hour, calculate the average efficiency of the power plant. So the thermal efficiency equals to 100 by MC into CV divided by energy, which is equals to 100 by HR. So that particular uh, conversion, 1 kilowatt hour equals to 859.8456 kilocalorie. So put that particular value. So thermal efficiency equals to 100 into 859.8456 divided by HR. So based on that, HR value is given 2600, and you get your answer as 33%. Some basic factors which actually affect the power efficiency are turbine types, boiler design, plant size, fuel heating value, and obviously the design parameters, the design choices. These are also very important factors which affect the power efficiency. And some basic thermodynamic also look at in the other class it is also discussed, some such as Rankine cycle and Brayton cycle. Those are the some basic cycles, thermodynamic cycles. I'm not going into the details of them. And also the if you overall if you want to classify the thermodynamic cycle, there are bottoming cycle, topping cycle, combined cycle, like that. Okay, you should check this particular thermodynamics actually conceptually, and from the examination point of view also might be important. And finally, if you want to calculate the overall efficiency of a power plant, this is nothing but the multiplication of the each unit of a particular power plant. So the overall unit efficiency equals to the boiler efficiency multiplied by turbine efficiency into generator efficiency into work efficiency. So these and all of these multiplications will go into the overall unit efficiency. Okay. So that is all from my side. Thank you for joining.
Okay. Can I give last answer, please?
Sorry.
Last answer can show you, sir.
The last question.
Okay, thank you, sir.
Okay.